البرنامج النهارده زي ما حضراتكم شايفين كده، يبقى الانترودكشن اللي بعملها البسيطه ديت، وبعدين هيتعمل ريكاب اللي حصل الاسبوع اللي فات من دكتور سمير، وكذلك هناك برضه لما اتكلم هيدي لكم برضه بعض الايه، بعض الاختصار للي حصل الاسبوع اللي فات. وبعدين الدكتور هيتكلم عن كورس sediment transport and profile evolution tool, the definition of shoreline change modeling scenarios, explanation of LitPack model simulations and scenarios, investigation of the shoreline changes model setup. طبعا الكلام ده كله هيبقى جاي مع بعضه، مش كنقاط. الدكتور سمير طبعا احرص واعلم مني بهذا الامر. فده اللي ان شاء الله هيبقى برنامج اليوم، اللي هو هيكون قصير حبه لان احنا بدأنا متاخر شويه في موضوع الطريق. ان شاء الله بعد ما الدكتور سمير مشكورا بعد ما ارحب حضراتكم جميعا انه يتفضل يبدا ان شاء الله. اتفضل يا دكتور سمير.
شكرا يا دكتور ابراهيم.
طيب كده
هنعمل ريكاب الاول كده، نراجع بسرعه عملنا ايه المره اللي فاتت. قلنا ان الليت باك بيتكون من 3 موديولز، والموديولز الى حد ما واحد ليت دريفت وده بيشوف الكرنت، واحد ليت بروف وده بيشوف التشنجز عمودي على الشط، واحد ليت لاين وده بيشوف التشنجز along لاين الشور لاين. وكل واحد منهم لاين يعني كل واحد وهو شغال ايه، مفيش يعني اللونج شوت كارنت مالوش دعوه بالكروس شوت كارنت، واخد بالك؟ ده شغال هنا وده شغال هنا. كونسرفاتيف اوف سيدمنت، يعني ده لو هو شغال هنا ما بيدخلش سيدمنت من ده. لو عايزين نروح كده لازم نروح لل2 دي. وقلنا الدريفت ده الليترال دريفت along the uniform beach، واتكلمنا عن يعني ايه على كروس سكشن بيبقى فيه فاريشن للكرنت نتيجه البريكنج اللي بيحصل. في حاجه اسمها البريكر زون، وده بيبقى في الاتجاه كده، ده الليترال كرنت، وحسبناها مع بعض بالبرنامج. الديستريبيوشن بتاعه دايما بيبتدي بصفر وبينتهي بصفر، وفي البيك بتاعه بيبقى اراوند البريكر لاين، والبريكر بتبقى زون. احنا نفس اللاين لكن هو زون، لان احنا عارفين ان الويف مش ويف واحده، دي كذا ويف، فكل واحده بتتكسر في حته، بيبقى زون كده ايه على بعضها. قلنا ان ده كله بيتولد نتيجه حاجه اسمها الراديشن ستريسز اللي هي اس، واس دي بتتحسب بقى ايه البالانس بارشل اس اكس واي بارشل اكس، هو اللي بيولد اللونج شور كارنت. معانا طبعا الدكتوره شيماء، هي في الطريق دلوقتي، هي واخده بي اتش دي بقى في ازاي تحسب الراديشن ستريس اس اكس اكس واس واي واي اس اكس واي، والكلام ده كله ايه ماثيماتيكالي. ف وقلنا اخرى من الكرنت بس 2 دي كرنت اللي هي الريب كرنت، بس ده مش هيخش معانا في الدريفت، لان ده 2 دي. ده بيجي نتيجه ان لو في بار يعني ايه، يعني حته تتكعبل فيها الميه الناحيه دي، يعني في حجر الناحيه دي، في حجر الناحيه دي، ومفيش حجر هنا. فبيحصل ايه؟ الميه اللي جايه هنا بتتكعبل بدري ودي بتتكعبل بدري، بيحصل فرق في الكرنت، اللونج شوت كرنت بيتغير، ونتيجه اللونج شوت كرنت بيتغير بيعمل الريب كرنت اللي بيسبب دايما اللي بيسموه السحب، انك انت اتسحبت دايما، ده اسمه الريب كرنت. وده اللي بيسبب التمبولو ده اللي بيطلع الظاهره دي. لو حطيت بريك ووترز كده اهو، فاللي بيحصل من الشط شور لاين كان عادل كده نتيجه الكرنت، نتيجه الفاريشن بياخد يسحب سيدمنت من على الشور ويدخلها ايه جوه، عشان المنطقه دي منطقه هاديه، والمنطقه دي منطقه فيها انرجي عاليه، فتقوم واخده من هنا وتلف لغايه ما يقفل على البريك ووتر ويكون الشكل المشهور ده. لو في بقى عندنا مينا، لو الجيتس كبيره قوي هتقطع الايه الكارنت، سيجمنت كارنت. لو جيتس دخلت عدت البريكر زون. فاحنا وده من الاخطاء الفظيعه انك تقطع السيدمنت ترانسبورت، ده خطا فظيع. ليه؟ لان ده بيسبب مشاكل على الشط جامد. في الحاله دي انا ما قطعناش ولا حاجه، فهو بيعدي. لكن طبعا ايه بيبقى هنا في شويه لو الكارد سيدمنت جاي من هنا بيبقى في شويه سيدمنتيشن هنا، وهنا في شويه ايه نحر عشان يعوض السيدمنت اللي اتخذت. ده مثال لجيتي طالع كده، فتلاقي ان الشط قبل الجيتي بيعمل سيدمنتيشن، وهنا بيعمل ايه نحر اروجن عشان يعوض الايه السيدمنت اللي وقفت. الحاجات اللي بتاثر على الدريفت، وهنا بنتكلم على ان الاوتبوت بتاعتنا عاده بتبقى بالشكل ده، دي الباثيمتري، وده الاوتبوت بتاع الايه السيدمنت ترانسبورت، الفيلوسيتي والويف هايت والووتر ليفل along the line. الاوتبوت بتاعنا بيبقى لونج شور كارنت بالشكل ده كيو. في منطقه جنب ده الشط هنا، ده الشط، وهنا في بيك للكرنت، وهنا في بيك للسيدمنت. وقلنا ان دايما عندنا حاجه اسمها بوزيتيف وحاجه اسمها نيجاتيف وحاجه اسمها جروس وحاجه اسمها نت. وقلنا الجروس هو مجموع الابسولوت فاليوز، النت هو مجموعهم بالشرط. وقلنا ان الجروس اهميته لو انت عندك مدخل هاربر فبيحصل سلتيشن على المدخل، فالجروس هو الموست سنسيتيف بالنسبه لك، لانه في الحالتين سواء جاي من اليمين ولا جاي من الشمال هينزل عندك رمل، يبقى ده ايشي. وقلنا ان النت لو انت بقى عندك شاطئ وايه وحساس بالنسبه للشاطئ بتاعك، ايه المشكله؟ واتكلمنا عن الكوليبريم، ان في ايكوليبريم لكل شيء معين. لو هو حاجه ستريت فعاده الايكوليبريم بالانجل. اهم معيار للايكوليبريم هو الانجل بتاع الميز اللي انت داخل فيها قد ايه. قلنا ان في شواطئ فيها انستابيليتيز، اللي هي زي الشاطئ اللي عندنا هنا في مصر. مش فاكر النقطه دي كان اسمها ايه. طول بطوس. بيحصل انستابيليتي ان بترمي السيدمنت بترمي بره خالص هنا، فبيحصل انستابيليتي كده في الشط بتاعنا. بعد كده اتعرضنا للبرنامج اكثر عمقا. قلنا والله انت مطلوب منك انك تحضر انك الليتباك. اتكلمنا عن الليتباك بس في الدريفت، انك تحضر الملف بتاعك، فانت مطلوب منك تحضر البروفايل اللي هو كروس شور بروفايل، واهم حاجات انك تديله الجريد سبيسنج بتاعك والنمبر اوف بوينتس، وانت مطلوب منك مينلي الباثيمتري. والحاجه الثانيه السيدمنت رين بارامتر، اتس نايس لو في فاريشن، لو انت الدايمتر بتاعك بيتغير تحط. وده كمثال للديف بروفايل بتاعي، ودي الدي 50 كونستانت في الاكزامبل بتاعي. السيجمنت والتايدل، لو عندك تايدل دخلها في الاعتبار، لان التايدز بتعمل في عمودي على الشط بتدخل بتاع 20 متر جوه وتطلع، فايه فازاي تحضر الووتر ليفل. ده دي اف اس 0 فايل، وده التايدل ليفل اللي هو اللي عندنا على الشاطئ بتاعنا لمده 40 سنه. ويفز مطلوب منك تحضر الويفز بتاعتك. مينلي بنهتم بالاتش والكين سكوير والبيريود والمين ويف دايركشن والسبريدنج فاكتور. السبريدنج فاكتور الحقيقه احيانا في بعض البرامج انت ممكن عندك وجهتين نظر في السبريدنج، اما انك تدور ديجريز عندي 10 زوايا 10 درجات، فانا داخل بكون في سبريدنج 10 درجات، او بتديله باندكس ان اللي هو بيتتبع الفورمولا كوزاين تو ذا باور ان سيتا 1 تمين ناقص سيتا دي بي. فيبقى ده يا اما تديله ان يا اما تديله انجل، والاثنين صح يعني على حسب انت عايز تحط ايه. فده بيسموه سبريدنج فاكتور، والثاني بيسموه دي اس تي دايركشنال مش عارف سبريدنج ديجري، دايركشن سبريدنج ديجري. الويفز دي بارامترز اللي ازاي نكريت الويف فايل، وكده دي كانت الحاجه الثانيه. وبعد كده عملنا illustration ازاي بقى تستخدم الورك فلو بتاع البرنامج. فبتبتدي ب اف ام ليترال بروسيس فليكسبل مش. قلنا دي مش ما بتفرقش كتير الدايمنشنز والباك جراوند ايمج. وبعد كده قلنا بتختار الاختيار بتاع ليترال دريفت. و اول حاجه بنعمل ريال تايم فورميليشن، نمبر اوف تايم ستيبس، ذا تايم ستيب انترفال. انت عايز تسيميليت كل ساعه، طب لمده كام ساعه؟ 100 ساعه، 200 ساعه، سنه، سنتين. عاده بنحسب الانوال، يبقى ده بيديني الافرج بالير بيحصل. طبعا هنا في السيميليشن بتاع دي اتش اي اللي انا بعرضها هو حسب الحياه بتاعت 20 سنه ولا 10 سنين ورا بعض. يعني حسب 20 سنه ورا بعض. اوكي؟ تايم مش كتير قوي. بتدخل له الفايل البروفايل بتاعك اللي احنا جهزناه، واهم حاجه الانجل بتاعك فيري سنسيتيف، فيري سنسيتيف بارامتر، فيري سنسيتيف بارامتر اللي هي الكوست لاين اورينتيشن. دي حساسه جدا للموضوع، لان دي اللي بتتحكم مين بوزيتيف ومين نيجاتيف وبناء عليه النت. اتكلمنا عن الانجل ديفينيشن بتاعها ايه، وعشان التبسيط قلت والله انا على حدود على الساحل المصري الشمالي عندي النورث، لو الشط كده يبقى الزاويه بوزيتيف 20، لو كده يبقى 340 300 على حسب، وممكن تبقى زيرو. طبعا في حاجه نادره قوي الزيرو ده. اوكي؟ وبعد كده اتكلمنا عن البيد ريزيستنس. لو كونستانت خلاص هتحط الفاليو بتاعتها، لو فاريبل بتحط بقى فايل في الايه في الريزيستنس.
معلش
اتفضل.
لو انا عندي يعني كل واحد كل حته في فوتوشوب ليها اورينتيشن مختلف.
مظبوط.
ازاي
ما احنا عاده بنحل كل يعني
الفايل ده ازاي؟
ما بنحل لاين واحد بس. يعني انا بجهز، انا هشتغل على الكروس سكشن ده، او هشتغل على الكروس سكشن ده، او على ده، او على ده. ولو عايز تشتغل مالتي كروس سكشن فالبرنامج بيقبل انجلز مختلفه. يعني انت لو فتحت افتح البرنامج بعد اذنك. اسمه
على فكره الناس مش في المال بتخطط تقريبا
بصي انا هنا قدرت احط different angles for different profiles. اوكي؟ يعني انا ممكن احط كذا بروفايل، لكن مثلا تقرير بتاع دي اتش اي الحقيقه كان بيتعامل مع كل بروفايل ستاند.
مش في انتراكشن بين البروفايلز دي؟
لا، كان بياخد بروفايل هنا، بياخد بروفايل هنا.
حركه سري.
ايوه.
مفيش اي كونتاكت ما بينهم؟
لا هو كان بيقول على البروفايل ده اللونج شوت كارنت شكله ايه؟ وهنا اللونج شوت كارنت شكله ايه؟ وبناء عليه بيبص للسيل اليونت من اليمين ومن الشمال. هنا كان دخل كام وهنا خرج كام، وبناء عليه يقول لك البالانس بتاع السيل دي غالبا بتخسر، يعني دي عوضه او بيحصل لها سيكوفيزيولوجيز، يعني بيديسكرايب السيل على بعضها كده. اوكي طيب
احنا بندخل بسميتي الواحد بس للبروفايل صح؟
لكل بروفايل بس
واحد بس
واحد
بس هو بيبقى معبر عن المنطقه ولا؟
لا ما هو بقى انت بتشوف اللي بيحصل على اللاين ده، فانت بتدخل البروفايل بتاع اللاين ده.
ماشي بس حضرتك السلايد اللي هي رقم 9 دي اللي احنا بناخد بروفايل تقريبا بيعرض
مش فاهم انت تسال تقصد انهي؟
اللي بعد الجايه. لا ايوه
دي
الجايه
دي
يعني دي انا لو في البروفايل مثلا وليكن اللي هو على غرب الدلتا او شرق الدلتا اللي حضرتك بتشاور عليه.
اوكي
ده اخد بس في بروفايل اسميتي واحد بس بيعبر عن المنطقه دي.
بيعبر عن اللي بيحصل في الحته دي، وطبعا لك ان تتخيل ان اللي بيحصل في الحته دي عكس تماما اللي بيحصل في يعني ربما مثلا المنطقه دي يكون بيحصل فيها نوع من انواع السيجمنتيشن. يعني انا لو واخد كده بروفايل كده وبروفايل كده، فدي منطقه ده بيرمي فيها وده بيرمي فيها. بينما لو جيت في منطقه زي دي ده بيسحب فدي
كل واحد ليه زاويه او
ايوه بالظبط. فدي ممكن تكون منطقه خطر، واخد بالك؟ ف مثلا كان مصاب من نهر النيل هنا مثلا، كان قاعد يجيب سيدمنت، فكان قاعد يرمي كده ويرمي كده يرمي كده. انت فاهم؟ شايف البيك دي ودي بيك برضه دي كده. وفي شويه رسومات في الكتاب اللي هو كان هندريك قال عليه. كان في انا بصيت عليه كده فلقيت جايب لك اللي حصل من 1800 كان قد ايه البتاع دي قاعده تدخل جوه، ولما توقف السيدمنتيشن بتاع السد العالي بقت الحته دي تحصل فيها تتاخر. ايوه بالظبط. لا والسيدمنت تتاكل، الراس دي قاعده تضمر. فاهمني؟ في الريبورت اصلا بص في السيدمنت في وجهتين نظر، وجهه نظر الساتلايت والانجينيرنج انتربريتيشن. يعني انت بتجيب سترايك ايمجز، ومن سترايك ايمجز تبتدي تقولي ايه اللي بيحصل في الشط ده خلال 100 سنه او 50 سنه دي. ده شغل كله سترايك واناليسيس للشغل لاين موفمنت. وفي وجهه نظر ثانيه اللي هي الليت باك. فانت الليت باك جبتي اللي بيحصل في اي سن، انت عايز تعرف اللي بيحصل من هنا لهنا، فجبت هنا وجبت هنا وتشوف هل السيجمنتيشن بتخش، يعني الترند بتخش ولا بتطلع. وعندنا بقى ندخل في الليفل الثاني اللي هو بقى اعمل البروفايل اللي بيحصل فيه بيتاكل، اللي احنا هنعمله النهارده بيتاكل ازاي. والليفل الثالث اللي هو ان شاء الله الاسبوع الجاي الشور لاين بيحصل فيه ايه، يعني بياخد من هنا يرمي هنا ولا بياخد من هنا، فاهماني؟ بس كل دي وان لاين موديل يعني كل حاجه اندبندنت. يعني الثيوري دي تكون الفاليديتي بتاعتها ليها ليميتيشنز كتير، ما يبقاش في 2 دي موشن، فاهماني؟ لكن قوتها ان التايم بتاع الكالكوليشنز بتاعها يعني عايز احسب 50 سنه، ايه اللي حصل في 50 سنه بتطور حاجات ثانيه، واخد بالك؟ ايه اللي حصل في 50 سنه في سنه. انما 2 دي هم 5 ايام، واخد بالك؟ يعني كونتيشنال تايم 3 دي. وزي ما قلت لكم انا وجهه نظري ان الثيوري اوف سيدمنتيشن ليست تعبانه، يعني مش ويل استابلشد، واخد بالك؟ وعشان كده بنلاقي المايك بيستخدموا جروبز من الناس مختلفه، ريسيرشرز باحثين، ودول تلاقي المايك بقى عايز يفنط لهم، عايز تلعب في السي 1 والسي 2 والريفل مش عارف ايه يعني ده ريسيرش. يبقى الجامعه بيحضر ماجستير عشان يشوف الايفكت بتاع الفيلز المختلفه وفي الانجينيرز مش هيخشوا في الليفل ده، فبياخدوا الايه الديفولت فاليوز. هو الديفولت يقول لك خد ده، واخدين بالكم؟ طيب الوتر ليفل عرفناه، وبعد كده الاوف شور الويفز بقى بنحدد الاوف شور. ممكن تبقى كونستنت لو انت هتاخد الدومينانت بتاعك او تبقى فانكشن اوف تايم. قلنا الاتش ار ام اس بيتحسب ازاي؟ جذر 2 اللي هو الاتش سيجنيفيكانت على جذر 2. وهنا السبريدنج فانكشن لو انت هتدخل ان، قلنا السبريدنج فانكشن دايركشن سبريدنج اما عن طريقتين، يا اما عن طريق ان يا اما عن طريق الانجل، حسب انت وانت بتديفاين عايز تعرف ده ولا ده. طبعا الانجل بتبقى مور وات سي، يعني الواحد يبقى فاهم حاسسها اكتر شويه. انما دي لو الان ب 2 فده سبريدنج، لو الان ب 10 فده، لو الان ب 50 فده، اللي هو قد ايه هي مركزه. فاهمين؟
المدى انتشار.
يعني هي وانا داخل الويف حبه اكتر من هنا وحبه من هنا، ولا كله واخد اتجاه بس. قد ايه هي منتشره. والانيوال ويف روز لو انت هتشتغل سنه واحده بس خليك سنه واحده كده. احمد عصام صح؟ ايوه. اتكلمنا عن السبيكترال ديسكريبشن، ان في نظريات مختلفه للسبيكترال ديسكريبشن، والويف بريكنج نظريات مختلفه للويف بريكنج. والسيدمنت انت عندك السيدمنت اما انك انت عاده احنا شغالين ساند، الثيريز بتاعتنا كلها شغاله للساند بس، اللي هو حاجه تمسكها كده رمله في ايديك، مش كلاي، مش حجاره، خلينا ما نتحركش. كلاي انتوا عارفين الكلاي طبعا، الكلاي ده لما تمسكه في ايدك يعني خليه مش نضيف، خليه تحس مش لذيذ. الرمله عادي كده تمسكها ترميها. الكلاي ما ينفعش معانا. اوكي؟ يعني الكلاي مش داخل بتاعتك. والله يا اما السيدمنت بتاعتك يونيفورم، فانت بتحدد الجريد سايز بتاعك بس، يا اما جريدد فانت بيبقى عندك كذا مستوى وهم متفقين، او تحطها على داتا فايل. بالداتا فايل بقى دي 50 على كروس سكشن، معروف ان كل ما تخش جوه كل ما السيدمنت انعم، فعلى حسب انت الداتا الافيلابيلتي اوف الداتا عندك قد ايه، والجريدنج كوفيشنت ازاي بتعرف. اهلا ازيك يا دكتور؟
اوكي كل تمام. الحمد لله.
اخباركم ايه؟ الحمد لله بخير.
الحمد لله. لا الحمد لله رب العالمين. الله يبارك فيك.
فده الجريدنج كوفيشنت. لو السيدمنت الجريد دايمتر بتاعك دي 50 فاريبل في الدومين بتدخله كملف دي 50 لازم يكون دي 50. والبيد البورستي بتاعت البيد قد ايه؟ عن النمبر اوف فراكشنز اللي انت هتسيميوليت عليها والوتر تمبريتشر. يعني انت لو عايز تاخد لو عايز تاخد نوع واحد بس هتحط واحد، لو 2 5 فبيحل 5 انواع من السيدمنت، كل نوع بيحل لوحده وهو فانكشن اوف تمبريتشر، عشان التمبريتشر بتقول بتافكت ذا فول فيلوسيتي اوف individual green fractions. عارفين اصلا هو الدي 50 اللي هو حجم السيجمنت دي لما بتحطها في الميه بتقع. طب بتقع بسرعه قد ايه؟ بيسموها الفول فيلوسيتي. طب الفول فيلوسيتي دي فانكشن اوف التمبريتشر، فانت لو تلج مش هتقع، واخد بالك؟ طب لو ميه سخنه قوي بتقع بسرعه قوي. فاحنا عايزين الفول فيلوسيتي لان وهي ماشيه هيحصل انها تترسب، فتفرق معانا كتير قوي الفول فيلوسيتي. سيتنج فيلوسيتي اللي هي الفول فيلوسيتي اللي هي سيتنج فيلوسيتي. ده النمبر اوف تايم ستيبس اللي انت الران تايم بيزيد اول لما النمبر اوف تايم بيريودز بتاعك بيزيد. دي الكالكوليشن بارامترز بتتوقف عليها الاكيورسي بتاعت الريزلتس. وبعد كده اتكلمنا عن الاوتبوت بتاعك بيطلع دي اف اس 1 فايل ممكن تطلع فيه الحاجات دي كلها. وده الباتريمتري وده النت دريفت، وده الجروس، وده الدريفت البوزيتيف، وده النيجاتيف. دي الاوتبوتس اللي بتطلع عندنا. لنا ازاي بقى تجهز الداتا بتاعتك دي اف اس 1 للديبس داتا وازاي تجهز السيدمنت والتايلر. بالتالي انا عرفت الحاجات دي خلاص صح؟ ما عرفت الكلام ده خلاص. Henrik, are you available now?
Yes, sir.
Great. Can you start recapping your previous session and then start our session today?
Yeah, I guess. Yeah. I didn't. Oh, I can hear again a very strong echo.
I will stop the voice from.
To be honest, I didn't prepare any slides on the recap part. I saw it in your agenda, but I thought you were sort of recapping the entire session 1, to be honest. So I can of course recap it, but how should we best possibly do it? I could look at the slides again.
Yes.
But I am also referring to what I presented in the first session because it was a general overview, right? And now we're picking the elements that we need for today. So, yeah. I think I will just add a few words in the beginning of my presentation, recapping my previous session without looking at the slides again. That's
okay.
fine.
Please go ahead.
Okay. Okay, I assume you can hear me and see my screen and the little cursor. Otherwise, please let me know. I can see a thumbs up. Thanks. My contribution to today's sessions will be to zoom into the cross-shore sediment transport in the context of the LitPack toolbox and the profile evolution tool. There was also a question last time how to then actually extract the cross-shore transport from the model, and that's exactly one of the outputs that is available from the tool that we're looking at today. And I'll just present a little bit the underlying equations and point out a few parameters. Introduction, then the table generator, which is one step in the model. I'll get back to that in a second. The quasi 3D model simulation of sediment transport in one point, which is the core of this whole profile evolution toolbox, but also the littoral drift that you guys just looked at with Samir. The profile evolution, and again, a handful of references. So introduction, and I'll get back to the recap in a second. No, don't worry. So what I'm looking at within just to sort of where we are for the content of this presentation, that's in the LitPack toolbox, and then the profile evolution tools consisting of the table generator on the user interface side, consisting of the table generator and the profile evolution. So the application, last time I gave a general introduction to hydrodynamics in the coastal area, the wave transformation, the currents and the water level setup, and they all are interacting, right? The wave transformation was, for example, leading to the water level setup, and also the wave transformation during the imbalance in shear stress was leading to longshore currents. And after, like, we discussed that a fairly big step in modeling sediment transport, both in the longshore and cross-shore direction, is actually to describe these hydrodynamics across the coastal profiles. And once that first step is completed, and that needs to be done in all the models dealing with the littoral transport processes. Once that step is done, the hydrodynamic conditions are resolved, then the sediment transport is actually modeled, like the suspension of sediment from the bed and the transport of that suspended sediment, as well as sediment on the bed transport. And we discussed there's two fundamentally different transport processes considered, and the one is a cross-shore transport, and the other one is a longshore transport. So the application of the profile evolution tool. So it models the cross-shore profile changes based on the wave conditions and actually also water level time series. Typical applications are the storm profile response or the response to beach nourishment. And one example here from my previous presentation was measured cross-shore profiles in Palm Beach, Australia. And we just go through that one more time. So it starts, the time series starts with the 28th of April, where we can see some dune landscape and also an offshore bar, and then a bit of a steeper profile. And then we have a storm event, and after the storm on the 28th of, on the 2nd of June, the black solid line, the offshore bar has disappeared. Material has, and also the dune part of the beach has been eroded, and material has been deposited further offshore. And then a year after the storm, so black was in the lower panel here, black was the storm event again, and then a year after, the blue line here, we are seeing an approach towards the discussed equilibrium profile. So the beach starts to replenish here, and then actually also the dunes over time, they are like a long-term reservoir of sand. Like a beach dune system is a very effective way of coastal protection, because for now it's only on the beach, but then over time onward wind towards land will transport this sand that's here on the beach back into the dunes, and also the dunes can restore. So basically, it's a constant back and forth between storm events and calm conditions. And only if if the substantial amounts of sediment are lost offshore, or we have strong gradients in the littoral, like in the longshore drift transport, then this balance might be disturbed, or of course by human interference, by placing structures on the beach, placing hotels in the dunes, etc., etc. So we're considered now with how this profile responds to different environmental conditions, and maybe also what happens if we place additional sand, like the nourishment, into such system. The assumptions are that the longshore gradients and the hydrodynamic and sediment conditions are neglectable. So we're not saying that the longshore currents are neglectable, or the longshore transport of sediment. We will also see that longshore currents are a part of the cross-shore model, but we're saying that the gradients are neglectable. And that is usually the case if the depth contours are parallel to the coastline. And there is an example here of the west coast of Denmark, so where really also the dominant wave direction is sort of in line with the coast normal, and there is no features along, no bathymetry features along beach, and also the contours are quite parallel to this beach line. And then in such a situation, the coastal morphology can be solely described by a cross-shore profile, which you can draw across here, saying if you draw the profile here and model the situation, or here, or here, or here, or here, it's basically everywhere the same. So that's a fundamental assumption in this model. So if you are concerned with very complicated situations, sediment transport around a reef, etc., you need to really be careful how you apply these tools, or maybe use other tools altogether. So the model structure is I try to put that a little bit in a flow chart. So we have the table generator. We saw it in the user interface, the profile evolution. And then under the hood, if you want, there is actually the transport in a point, the STPQ3D. And that, how does it go together? It works like that, in the table generator, well, we start actually with the profile evolution tool here on the right, sorry. So let's say you have a time series of offshore wave conditions, right? And now you're interested in the time series of the transport and profile evolution. Then the profile evolution can transform the offshore time series to the hydrodynamic conditions across the profile and compute the sediment transport, and over time then also compute the profile evolution. However, calling the transport in every single location along the profile and every single time step would be very time consuming. So instead, we pre-calculate transport tables where we can then simply interpolate from. And for that, we use a table generator. So the input to the table generator is a user-defined envelope of hydrodynamic conditions. So you basically just say wave height 0 to 10 meter or 5 meter in this and this step, etc., etc. And then for all these bins in your tables, it's a multi-dimensional table. We'll look at that in a second. For all these conditions, the table generator subsequently calls the transport in one point to what these hydrodynamic conditions in a point are the input, and gets the transport rates and then tabulates that. So let me just read through the bullet points here to reiterate that. So the table generator calls the sediment transport program to tabulate the transport rates for an envelope of hydrodynamic conditions. And the profile evolution has actually a couple of steps in it. It does a wave transformation across the profile, including the shoaling, refraction, bed friction, and wave breaking. It computes the longshore currents due to the wave-induced radiation stress. We also discussed that in my first presentation. And then it does not compute the transport, but it just interpolates the sediment transport from the tables that we already computed. And then finally, it calculates the bed level change from the continuity equation. And now for the remainder of my presentation, I want to go through these three components. So we start with the table generator, and you'll see I'll do a bit of a mix of equations and also GUI screenshots to just show some parameters where they are in the GUI. But the screenshots that I'm presenting of the GUI are not necessarily step by step of how you set up a model, because we have a lot of sessions that are more concerned with these hands-on examples of, okay, how do you actually set up a model? I try to put it in an order that makes most sense, hopefully, in terms of the concepts behind it, and then where you can find the parameters. So the table generator. So now in that flow chart, again, now we're looking at this guy here. As said before, to reduce the time for simulating the profile evolution, the rates of the sediment transport are tabulated for various combinations of the input. And then the tables are generated by successive calls of the transport in the point model. And transport tables are input to the profile evolution. So because that is so, there is actually no direct interface for the user exists to set up a transport in a point model. Like you cannot, you can in the toolbox, in the mic toolbox, you won't find an item transport in point model, because it's only called by the table generator or by the lit line that Samir just presented before. So that means all the settings of how the transport in a point is computed is defined in the setup of the table generation. And then on top of that, in the table generation, you need to define your envelope and your outputs, etc. So in the table generator, there's sort of like input of some overhead, and then the direct input to the transport in a point model. So the dimension of the transport tables or the envelope of the conditions is the one input that you need to define. And that's happening on this screenshot that I put here in the transport tables. And basically these parameters here on the left, they are all the input to the quasi three-dimensional sediment transport model. So we have alpha, the deep water wave angle. We have the wave height. We have the wave height to water depth ratio. We have the wave period. We have the bed slope. We have the dissipation rate. We have the longshore current. And we will, once we look at the profile evolution tool, we will find some of these items again. But basically, for now, we just know that these are the inputs to the 3D transport model, and I simply tabulate them from, for example, the wave height. We go from 0.1 meters in 8 values up to 1.5, and then I just have a scatter table, and it's a seven-dimensional table, right? So you need to it can take some time to compute these. So you need to do some engineering judgment here, which values are really required, which also, of course, depends on your offshore conditions later. Like there's no need to compute to for example, the wave height. There's no need to compute to very large waves if they don't occur in your offshore time series. On the other hand, the largest waves will just be taken from the last spin. So if you're too small here, your available results for transport rates will not be correct. And one thing more to notice here, the table generator tool and later the interpolation makes use of symmetry. So the wave angle only has to be defined. So the wave angle, I saw a screenshot by Samir just before. So recall that's the angle between the wave incident and the shore normal, and it only is defined from 0 to 90 degrees, and then from 90 to 180. All the shear stress, etc., it's symmetric, so it just repeats itself, and then just with another sign. So instead of positive transport, you get negative transport. So again, to save computation, we only compute it from 0 to 90 degrees and use symmetry. And then the output. And now I jumped over quite a few things in the table generator, because we'll get back to that when we look at the formulation for the transport in a point. Then we look at all the other settings that are needed for that model in that context. But the only other setting you need to do in the table generator with regards to the overhead, I called it, are the output definitions, and they are. These are the cross-shore transport and the long-shore transport tables. So they contain the sediment transport capacity in solid volume rates for each combination of the parameters that we defined before. And the solid volume rate, we will call that again. We will hear that again later. It's just important to keep in mind what quantities we're actually looking at. Yeah, and these you just need to. That's more like a workflow thing then, but you just need to recall that these tables will be needed in your next steps, so you save them somewhere in your workflow where it makes sense to them. Call them again in your profile generation simulation. And now we come to the quasi three-dimensional sediment transport model. So it's a core. So it's that guy over here that's called by the table generator. And it's a core of the sand transport modeling in combined waves and currents. And it is actually also called by the LitPack FM modules. So So it models the temporal and vertical variation of the shear stress, turbulence, and flow velocity in one point. And then you basically, you call, and we will see that a little bit later, then you call that model along multiple points along your cross-shore profile to then get the cross-shore profile of transport rates. But here within that model, we're only looking at one point. And recall that right now, when the table generator calls this, it doesn't matter where we are on the profile, right? Because we just call it for an envelope of hydrodynamic conditions. We just call it for, if I have a wave height of 1 meter with this incident angle and at that water depth to wave height ratio, then my transport is this and this. What the profile looks like and why I am in the along the profile is not a concern at that step here. And the model models the bed and suspended load separately and sums it to the total load. The concepts of the bed load and suspended load was also something that I mentioned on the first day. So the vertical velocity profile, the time average flow velocity, U bar, is found from the force balance equation. So we have the fluid density, we have the viscosity, we have the gradient vertical velocity, horizontal velocity over Z, so the vertical profile of the horizontal velocity, and that's balancing the horizontal shear stress, the vertical profile of horizontal shear stresses. We assume a no-slip condition at the bed, and the forces include the contribution of the near bed wave orbital motion, the wave braking, and the wave setup. And that's the average flow velocities. And by the way, I just from the manual, the vertical resolution of the numerical grid where that force balance equation is solved. It's using a log spacing for the first 10% of the water column, Z over D. D is the water depth, and then a linear spacing for the rest. And there is a formulation, I didn't put it here now, but it's actually sort of choosing based on the sediment conditions. The point in a transport and point model is choosing the grid resolution. You can read about that in the manual, but usually you just go with the defaults. And then we also have the instantaneous flow velocity profiles. So let's just quickly recall what that, which is modeled from it for the turbulent boundary layer for the combined wave and current motion. And the model I provided here, the reference, I will look at a little bit at it, but we don't go into details of the governing equations for that. I mean, it's almost a science in itself. But let's quickly recall what is now the difference between the instantaneous flow velocity and the time average flow velocity. So that when we have offshore conditions, offshore wave conditions, we will have a time series of like 1 hour, right? And then within that 1 hour, we will have individual waves of a period t. And then the time average flow velocity is averaged over the wave period, whereas the instantaneous flow velocities are at instantaneous points within the wave period, because it's actually, as you know, orbital motion of waves, the velocities will actually be changing direction, etc. And we will hear that again a little bit later, that difference between average and instantaneous and how then that is handled to actually derive sediment transport. So as I said, I won't go into details on the shear stress, but just an overview of what sort of different components are considered in the shear stress. And now again, we we're talking now about the vertical profile of the shear stress. So, well, we have a time average shear stress. So basically, we have these three contributions. The time average shear stress, so averaged over one wave period, associated with the wave motion. The shear stress associated with the wave breaking, and that's basically transported through the water column. So we have an energy insertion at the top where the wave breaking happens, and then it's linear or constant throughout the water column. And then we have a shear stress due to wave setup. We discussed a wave setup that due to the wave breaking, there is an imbalance on cross-shore shear stress that has to be balanced by an offshore current, the undertow, and that offshore current is driven by a water level setup with slightly higher water levels near the coast than offshore. And the shear stress associated to that wave setup is basically just the hydrostatic pressure. So it's a linear profile. And then we have the resulting shear stress distribution, which is shown here. And that is basically the input or the left-hand side of the force balance equation, which is then numerically solved for the distribution of the mean flow. And then we had the in the force balance equation the eddy viscosity or the turbulent viscosity, this term here, and that eddy viscosity has a couple of different contributions. One is in the wave boundary layer, the first term here, and that's a function of the friction velocity and the boundary layer thickness. And again, I won't go further into detail of the model formulations, but there is actually a model inside the transport in a point model that is modeling the evolution of the boundary layer thickness. So internally, we will get different instantaneous thicknesses of the boundary layer and also different instantaneous friction velocities over the wave period, because it's also changing directions. And you can imagine that a boundary layer develops and then the flow is returning. So the boundary layer is destroyed and then it has to develop again. And then we have a turbulence from the mean flow. And we all know that just from normal hydrodynamic modeling. And there is a mixing length formulation used. So the larger the vertical gradient of mean velocity over dz, the larger this contribution here. And then we have the wave breaking contribution, where K in this case is a turbulent kinetic energy and not the wave number, and then a production term. And the production term is the energy that is dissipated during the wave breaking. And we will get back to that when we look at the wave breaking model that is applied in the profile evolution toolbox. So that is along the profile. Now we are only at one point, but along the profile we simulate or model the wave breaking and thereby the energy dissipation. So when we then only go into one point, which we're looking at now, this production term here is simply an input to the model, and it's actually in the table it's called dissipation. So the terms production and dissipation is the same. So when we think in the context of breaking, the term used in the manual and the user interface is dissipation, because I remove energy, and in the context of eddy viscosity and turbulence, it's a production term because I'm generating energy. but it's the conservation of energy. So these guys, two guys, are the same. And then in addition, it's an eddy viscosity is added due to the wave-induced ripples. So when you have wave motion, you create the small sand ripples, and that, as you can imagine, will have an impact on via an apparent friction on the mean flow and also on the development of the boundary layer. And there is a model to model these ripples also included in the sediment transport model, and then a corresponding additional viscosity. But it is advised that this you just need to be aware of that can be done, and just choose if you turn it on or off, but usually it should be on. And it is also advised to go with the standard model parameters here. Like there is not really any data available to calibrate that further in practice. And now we also heard that in my first presentation. So now to model the wave kinematics in the water column of waves in intermediate and shallow water, or in the coastal zone in general, various wave theories are available, and it depends on the situation you're in, which one is applicable. But the ones you can choose from here in the transport model, which is then again this screenshot here is from the table generator toolbox, which is defining the input to the sediment transport model, is the Stokes, the conoidal, vocoidal, and two empirical formulations. And it is really, experiments have shown that the skewness, so of the velocity distribution, so the imbalance between the positive and the negative velocities of the orbital motion, they are very important for the cross-shore transport. And I think that's also intuitive, right? If you have much smaller negative velocities, so offshore velocities, than onshore velocities. In the graph here, by the way, we're looking at the a near bed velocity over the wave period, so from 0 to 1 on the time axis for the 5 different wave theories. Then if you have this peak here of positive velocities and milder negative velocities versus the perfect symmetry for the Stokes first order, it is quite intuitive that the resulting net transport will be affected by that. And what is used in the model is or available in the model and used by default is an empirical or parameterized expression, which is including the velocity skewness as a parameter as a function of the Ocel parameter. And then there is later, this has been extended to also include the bed slope. So this usually here at the bottom is what I would advise to use. And then finally the model, well, the actual output that we're interested in is, of course, the sediment transport. So after now the hydrodynamics in the water column have been resolved, the total transport, the sediments transport, is computed as the bed load and the suspended transport, and then the total transport is the sum of the two. For shingle-sized material, there is only the bed load computed, and for sand, which I assume is most relevant along the coast of Egypt, I would assume, is both the bed load and the suspended load is calculated. The bed load is calculated from the instantaneous Shields parameter. I didn't put the formulation here, but you can find it in the scientific documentation if you're interested in. further reading. The Shields parameter, we recalled that in my first slide, so that was an indication or parameter for sediment movement as a force balance between the impacting force on the sediment and the resistance of sediment particles. And the vertical variation of the suspended sediment concentration is calculated from the vertical dispersion equation. That is, the dispersion equation is quite a well-known formulation from any sort of spreading models. And in this one, to then disperse the suspended sediment, we kind of need an input or a source at the bottom, and for that, again, there is a formulation used for reference bed concentration, which again depends on the Shields parameter. And these are so the Shields parameter and also the velocity inputs to these model steps. They are all the instantaneous values. So really for a number of time steps during the wave period. So the wave period is broken down into smaller time steps. So we will get a little bit of sediment in the one direction, then in the other direction internally in the model. But then finally, the suspended sediment transport is integrated over the wave period and over the water depth. And then here you can see we have a concentration time instantaneous velocity integrated. So here we have then a convective term, which is why the convective term is omitted in the dispersion model. You also have the opportunity to model graded sediment. So the uniform sediment as the most simple input is solely described with a median, there's an N missing here, sorry, grain size D50. So the Shields parameter, etc., refers to that D50. But we can also describe the sediment by a curve, a log normal grain curve as a function of D50, and then a geometrical deviation. And the geometrical deviation is the square root of the D48 and D16. And for it's presented here at the top right for different geometrical deviations. So the larger the geometrical deviation, so the larger the ratio between the D84 and D16, the larger or the more flat the grain size curve. So it is also a good idea to look at these sieving curves and to get some local samples at the beach where you're modeling, and then from that using some engineering judgment or maybe some sensitivity tests, you will have to choose how you represent your sediment in your model. And then along these, that's the theoretical distribution, and then along that you also need to choose the number of fractions that you actually model. So for each fraction, then the previously discussed sediment transport will be computed and then added up of all fractions. And again, the description of the parameters is part of the table generator, where the sediment transport conditions are defined and then passed on to the sediment transport model. So, and then the driving parameter in the formulations for suspension, or if the sediment gets suspended under the wave action, is the falling velocity. And the falling velocity is a rather long expression, but it depends on the relative density between the fluid and the sediment, which is S, on the grain size, on the viscosity, and a few other things. And the viscosity, again, depends on the temperature. And hence, you're putting in the water temperature here at the bottom. So that here will have an impact on the viscosity, which will have a small impact on the rising velocities, the falling velocities, and hence how much will get into suspension. And this is the formulation that's used when you use a graded sediment. There is so here shown as an example, D1, D2, D3, D4 are these discrete sediment fractions that you're considering, and that are in this case are coming into suspension. So based on the maximum ratio between the maximum friction velocity and the settling velocity of each sediment fraction, it is decided if it's coming, that fraction is coming into suspension or not. And with that, you can also define a critical particle size. And that again is computed instantaneously. So there might be some suspension for some fractions of the sediment for some part of the wave and not for other parts of the wave, and then it's integrated again as shown before. And another parameter in the context of, usually you don't really change that, but just to mention where that comes from in the context of sediment transport, is then the critical Shields parameter. And we also looked at the Shields diagram on the first day, and it is the critical Shields parameter is a function of the Reynolds number, as I said, but here in the model it's actually a user input, which is usually set between 0.004 and 0.006 with the default 0.045, and the 0.045 is, I indicated here, is exactly that plateau where the critical Shields parameter is constant for the high Reynolds number regime. So usually we are over here, but as you can see in this whole Shields theory, there is also some scatter of the experimental data that informed this curve fit here. So at the end, it is also a calibration parameter if you happen to have data available that allows you to calibrate this. But usually you would just go with the default. And now we come to the profile evolution tool as the last main section of this presentation. So just a recall, we've now looked at the table generator tool. In the table generator tool, you define the envelope of conditions and you define where to save the output, and also you define all the parameters that are used by the transport in one point, because the table generator calls this transport guy several times to build this table. And now we come to the profile evolution, and it initially said it has a few steps. So the one is the hydrodynamic model. It does a wave transformation across the profile from the offshore time series, which is the input, and includes shoaling, refraction, bed friction, and wave breaking. All of these conceptually discussed in the first session. And it also computes the longshore currents due to the wave-induced radiation stress. After the hydrodynamics are solved, we come to the sediment transport. And that then, in this case, only interpolates the sediment transport from the tables. So along multiple points along the profile, it then looks up or interpolates the corresponding transport from these transport tables, both the longshore and cross-shore transport. And then it smoothes the transport field with a cross-shore exchange factor, and that's quite an important component that will impact on your results, and we will look at that. And then as a final step, there we have the morphological model, which is a simple continuity equation consideration that then calculates a bed level change along the profile. So along the cross profile, when we have multiple points where we have the transport, there will be gradients in the cross shore transport rates. And if you have in one point more material coming in from offshore, then transported further to the shore, your sediment will build up. If there's a negative difference, your sediment storage or your will reduce. And then by doing that, your profile evolution is actually updated. And that means that in the next time step, the new profile is also used in your hydrodynamic model. So your hydrodynamic model, which models the wave breaking or the wave transformation over your cross-shore profile, is not using the profile that you initially provided, but is using the profile that has developed over the course of the simulation. So now we look at these components in a little bit more detail. So for the profile evolution, you need to define the cross-shore profile, which is sort of the initial condition, if you want. I mean, if you recall that example of Australia, Palm Beach, where you have the three measurements. I mean, you can use some sort of average of that, but maybe you only have one measurement, and maybe that one measurement is after a long calm period, or maybe it's immediately after a storm. So that sort of initial profile that you provide here it's only one snapshot, right? And then from there you let the model go and develop its own profile that corresponds to the environmental conditions and the sediment type, etc., that you assume. Well, the cross-shore profile, you will also look at that in the hands-on a little bit more, but it has a bathymetry, of course, is the depths, bed roughness, and a non-erodible bed you can put in, because in some areas you might have a clay layer or something similar. And actually in Egypt, that is, to my knowledge, also relevant, that the available sand or the available sediment to transport is much below the potential transport. So you have underlying to the morphodynamical changes, you have underlying some fixed bed which cannot be changed by these processes. And that's important to consider, because if you don't define that, the model will just assume infinite supply of material. But that infinite supply of material might not be there, because there might be geologically another layer present where no sand is offered to the dynamic process. And the mean grain diameter and the geometrical spreading can be defined. Then here there is the angle of the normal to the coast. I don't know, I didn't put a red mark around it, but to be honest, I've never quite understood that. In the manual it reads it can be used for a quick assessment of the sensitivity if your wave incident angle changes, but then you should change the wave direction. Like if your orientation of your coastline changes because you input some structures, for example. I mean, that's a core of the assessment that we're doing. But the normal to the coast is always 90 degrees, right? That's the definition of a normal to the coast. So this just sits at 90 degrees. The cross-shore grid spacing is 1 meter, but actually there is also some routines in the model if that's not sufficient. Depending on the gradients in your profile evolution, that is also changed under the hood. So this is sort of like an initial setting, and you can use the default as a starting point. And then there's a clay layer option. So even if you include a non-erodible bed here, you still need to say here included also. Otherwise, it might be in your profile file, but you might not be losing it. And if you say yes, it will use the item 3 of the profile, which is then the Z position of that non-erodible layer. And then there is the energy loss due to bed friction, and that usually should be included because it's relevant in the shallow water. Then we have the offshore conditions to be defined. So it's a time series, a DFS0 of climate, and Samir already discussed it a little bit. You already pointed out, and I also put it in bold here, that we're looking at the root mean square root wave height definition. So that's not the wave height that comes out of the spectral wave model, which is the spectral estimate of the significant wave height based on the zero order moment, HMO. So you need to convert that, and I already saw the equation provided by Samir. And then after I've now defined this offshore wave conditions, these wave conditions are in the hydrodynamic model transformed over the profile. And the cross-shore variation of the wave height is calculated from the wave energy equation. So we have the component of the energy in the shore normal direction, the cosine, and we have two sinks of energy. You can say the one is the dissipation due to wave breaking, and the other one is the energy dissipation due to bed friction. The energy flux, so the propagation of the energy across the cross-shore profile, is computed from the linear wave theory. Not going further into the details here, but we have the wave celerity, we have the wave number, we have the water depth, and we have the H mean square. We have the fluid density, and we have the acceleration due to gravity. The dissipation due to wave breaking is available for regular waves and for irregular waves. But I would say for most practical applications as engineers, we're concerned with the irregular waves, where the regular waves are more reproduction of laboratory experiments and for maybe calibration or model development purposes. For the breaking waves, the Batjes and Janssen model is used. And the dissipation is the dissipation, and we recall that this dissipation was an input to the table calculation tool and was the production term of turbulent energy due to wave breaking in the turbulent eddy viscosity term. And there's a formulation used that is based including a fraction of breaking waves. And the fraction of breaking waves is defined as such, where HMS is the root mean square error wave height, and then some maximum of non-breaking waves, HM. And that HM is defined, has two calibration parameters, which are also available in the GUI. And that's the gamma 1 and gamma 2. So the gamma 1 controls the wave steepness, and the gamma 2 controls the limiting depth condition. So with these two, usually it's a 0.88, and the new default, this might be a screenshot of an old one. The new default for gamma 2 is 0.8. So if you change these parameters, you will have an impact on where on how rapidly your energy is dissipated, which will have an impact on the distribution of your cross-shore transport and the development of the bar, etc., etc. And then, an important aspect are the surface rollers. In my first presentation, we looked at the, just for information, I think I have about 10 minutes maximum back, so it will be a roughly an hour presentation. So otherwise I would have suggested a break, but I think now we just take the last slides. We looked at the different processes for wave breaking, and the surface rollers were those where the braking is initiated, but then sort of the water dribbles down and you get a lot of whitewash, and that happens over the length of multiple wavelengths. And that means that that of course the generation of energy is spread out in the horizontal direction. And the formulation that is used here for the surface rollers is given here. And it's sort of an energy or a balance equation of some area where the surface roller is active, and and there is an empirical constant, the beta, and that one is quite an important calibration parameter, because this theory of surface rollers that has been based on the laboratory experiments, and there the roller coefficient factor beta has been found 0.1 to 0.2, but that leads to too small roller areas for irregular waves. So for irregular waves where you have the directional spreading, etc., these areas where you have the whitewash are much larger. So the energy or dissipation is spread over a much larger area. And then some experiments indicate, that's from the manuals of DHI, that 0.005 might be adequate for irregular waves, but there is not a strong data set exists to really choose that. But you need to keep in mind that this default 0.15 is for regular waves. And then some further processes are handled by the HD model, the longshore currents, which is also the input for the transport in a point, as it is relevant for the turbulence, right? The turbulence in the water column doesn't of the mean flow doesn't only is not only generated from the cross-shore current, but also from the longshore current. Then the directional distribution of the waves and the wave setup and set down. And there is one example here also from the manual where we can just see a few aspects. So if we have a profile like this, there's an offshore HMS, then the hydrodynamic model will be able to model a slight increase of that wave height due to shoaling, right? As the waves propagate over in the initial part here, they start to increase. And then at some stage there will be the breaker line. So waves start to break, wave height decreases, and the decrease of wave height and the breaking and the imbalance and shear stresses, and also a mass transport will lead to a little water level setup, especially just close to the shore. And that setup of water level will again, as a hydrodynamic pressure, contribute to an underflow. We have the longshore transport velocities. They have a maximum over the bar and then close to shore, and then of course 0 at the shoreline because there's no water onshore, which is also true for these other two graphs. We have the dissipation of energy, and that is now the interesting one, that including the roller, we sort of have a horizontal, a spatial shift towards the shore. So the dissipation of energy is initiated in the same point at the breaker point, but then it kind of continues longer because the water, like that white, was dribbling down the waves and being transported over several wavelengths. So that means that the maximum of energy dissipation is reached a little bit later. And again, this now is negative. So now we think in the terms of energy dissipation. So I take energy out of the wave system, but in terms of turbulence and input to the water column, this is a production, right? That energy is absorbed by the water column. And then there is the cross-shore exchange factor. So after the profile evolution tool has queried the transport in multiple points along the profile, it's sort of discrete points, it needs to take care of some diffusive effects, and it's quite easy to envision what these diffusive effects are when you consider the example of a breakpoint of a regular wave. So if you have just a regular wave, even in an experiment setup, which breaks at the same point all the time over many hours, the flow and the sediment transport, and also then a development of a bar, etc., they will be smoothed out, right? So there is some diffusion of the transport happening, and that's the same concept also is true for irregular waves. And in the model, this effect is basically taken care that after we have the transport in the. Okay, welcome to the rest. So I hope that everyone arrived safely then by now.
Thank you. Thank you.
So the same effect we have for irregular waves, and in the model that is taken care by basically just averaging, doing a rolling average over the transport in these individual points in a length scale formulation. So which is proportional to the wavelength. So we have the wavelengths 2 pi over wave number, and then an alpha scale factor, and then we get some sort of a length in meters, say 50 meters, whatever. And then we just average, we do a rolling average over these transports in the individual points. And with that, the alpha scale becomes a calibration parameter, actually, if you have any data to calibrate to. And you can, this is from the documentation. So for alpha 1.0, which is the default, we have quite a smooth bar. And if you decrease the alpha, so you're decreasing the length over which you smooth out the transport rates, you get a very steep bar. And if you increase it, you smooth out the transport in the individual points. Like, let's say you have caught the transport, the point in the transport model every 1 meter, right? Then you have these transport rates all along here. If you then increase alpha above 1, you will average out over a longer distance and thereby smoothen your profiles further. So as you can see here in these examples, the response of the profile has quite visible to alpha. And the last comment on this is even more like a sort of a self, what's the right word? A self reinforcing phenomenon, because if you then have this steeper bar developing, that will also have in the next time step, it will have an impact on the hydrodynamic model and the hydrodynamic conditions that you compute. So it will lead to more concentrated wave breaking, and more concentrated wave breaking will then again lead to more concentrated cross-shore sediment gradients, and it will self-reinforce this effect. So this is if you have any historical information available of bar locations, this is worth to have a look at, to ensure that you're not entirely off, right? If you, for example, have a bar developing to just 30 centimeters under the water level all the time of your simulation, but the locals tell you, I never have a problem going out with my boat here because there is never a bar, then you could consider it playing with this parameter. And then the transport tables need to be defined. I said before, we have computed now the transport tables, which are independent of the locations because they are simply as an input taken hydrodynamic conditions, energy dissipation, etc. So the transport table doesn't know where we are, if you want. And then we just interpolate it. And then there is this little guy here at the bottom. It's the sediment porosity. So the transport tables are solid volumes. But then in the continuity equation for the seabed evolution, so that's the change of the seabed Z over time, is a function of the gradient of the transport. So input minus output you want. And then there is also the porosity in here, because if you have a 40% porosity, your sediment takes up more space, right? So the solid volumes from the transport need to be translated into how much space that takes into the vertical position. And by the way, for the continuity equation, there is, of course, the change in storage. So how much sediment is in my small control element is, of course, only a function of Z, so the vertical expansion, because it cannot expand in the cross-shore direction, right? Because then there's my next control element next to it. So the only direction, if I have a sedimentation of sediment in a location, the only direction is up. And closing now, without going into more details, is there's then finally also the available to consider some structures in the coastal profile. So revetment, submerged breakwater, or beach nourishment. Beach nourishment is basically you place an initial additional amount of material on your profile, which can have different sediment properties, or submerged breakwater as indicated here. A little bit effectively, it's like a clay layer, but it's more local, and that can have a sharper edges, etc. So there is some options here to include. And yeah, that was my last slide, and the references that was taken today. Again, a few initial plots again from the shoreline management guidelines, and then the DHI documentation is also quite comprehensive. And then with that, I would suggest open the floor for if there are any questions, and otherwise you will probably return to this with some hands-on exercises at some stage.
Thank you, Henrik, for your great presentation. Is there any questions about the theory? I know that the theory and the equation is a little bit complicated and not nice for engineers. But if you go more deep in this theoretical background, you can understand which value and what is the effect of every calibration factor. عشان انت تسالوني ده انت تحط كام انا اقول لك ما اعرفش. عندي سؤال بس. اوكي.
هو ليه دايما السيجمنت اللي بتظهر من البروفايل يعني سنس برضه طبعا ليه ما فيش جزء مثلا بيمشي مع النيوترال كارنت او النيوترال كارنت؟
لا دي one. I'm sorry, there was تجاوبك يا باشا. The one question about why the sediment for the cross-shore profile only moves in the profile direction and not going for the long-shore current or the long-shore direction.
Well, we're only modeling. We do model the transport rates in both directions, and we also model the currents in both directions, because also the longshore currents has an impact on the wave current interaction and the turbulence. But we're only considering the cross-shore component of the sediment transport having an impact on the profile evolution. And that's basically a model assumption and thereby also a model limitation that I mentioned initially, that this model can only be applied if the longshore gradients, the gradients of the longshore transport are neglectable. So we can have substantial longshore transport, but just the input and output into the profile that we're considering. So it's kind of normal to the profile that we're modeling. The output and input just needs to be balanced and small compared to the cross-shore transport. So there is in this setup here, in the toolbox, there is not a coupling. There is no coupling in between neighboring profiles, if you want. So it's not like a it's not a 3D resolution of your coastline. It is limited to long, uniform beaches, as initially shown for that west coast of Denmark. So where basically the dominating processes are happening in the cross-shore profile to explain to model the cross-shore evolution. And that means also going a little bit. I'm actually also now sitting with a project in Egypt. There, of course, you can find a lot of locations along your coastline. You have your tooth like this sort of zigzag shape. You have a dominating direction but of course you can very locally find situations where you might not get answers with such a profile simulations, because you have very complicated three-dimensional transport mechanisms around a reef or whatever, or peninsula. So I hope that answers your question. It's like all these tools that we have as engineers, like this is one. It has its strengths and its weaknesses. So you need to be aware as an engineer that you use it in the right context. Does that answer your question? Otherwise, please.
Simply he talking about one line. So one line in the cross-shore, you make conservation of sand on this cross-shore. And when you talk about along-shore, you make conservation of sand along shoreline. So you cannot mix between two in these simplified models. Otherwise, you have to go to more detailed 2D sediment transport models. But this has the benefits of fast computations, but simplified for within certain physical situation, not complicated 2D sediment transport. Okay. Is there any other questions? Yeah. To use this, yes. To use this model, the gradient along shore should be small. Yes.
But you can, of course, as an engineer, also still use it in a situation where you have a longshore transport. Like you can, for example, have a longshore transport evaluation, and maybe you do some beach nourishment, and then you have another model where you're assessing then how your coastline evolves, and then you use this tool to just for example, model the response to an isolated storm. So maybe you only model some weeks, and then within that time series you're looking at, you just need to be sure that within that time scale, the long shot transport can be neglected, right? So it always, and you can again use then the advantage of fast computation, right? Yeah.
Excuse me, I have a question here.
Yes.
You mentioned that we use this we can use this for storms. So generally speaking, we can say that LitProf used for storms. However, line used for what I say for long periods.
No. Sorry, then that was a misunderstanding. Like it is also in long periods, because the storm response might be very short, immediate, but then the rebuilding of the shore might take long time, especially in Egypt when you have your available sediment transport at 10% of the potential transport. You know, you might have a small sheltered beach that builds up over 5 years, and you only need a single storm from a slightly different direction, and the beach disappears in 1 day, right? So the disappearance of the beach you can model in 1 day, but the replenishment of the beach is still might be a long-term process, right? The timescales really depend on where you are and the local conditions.
Okay, great.
But what you cannot do from this profile evolution toolbox standalone is then the generation of the tables that would be used in the coastal evolution, right? Then you're in the package of the littoral transport FM. But the underlying models and the underlying formulations, and also calling the transport in one point, that's the same. Like you will see the same input parameters. So.
Okay. Yes, any other questions?
تايم سكيل عشان وين حيث التايم سكيل دي؟
لو في ستورم قليل زي one day، ولكن لو انت عندك لون بريود برضه تشتغل عليها عادي. يعني هو بيقول لي it's valid to use it for 1 day storm or 20 years. Yes. Okay.
A short term. Oh, sorry. Maybe just adding to your point before we go to like a short term application. A short term simulation might be, if you want to place a beach nourishment, an initial nourishment, like a huge amount of sand under maybe even a partly stable bathymetry, like with a clay layer, and you want to assess how resistant will that be to a 50-year event, right? Just to see, okay, if I place a beach nourishment and a week later I have a 50-year event, how much of that nourishment will be left? That question I can answer with a very short simulation, and that question I can also answer with neglecting the longshore transport, because I am just interested in that response of that nourishment to a storm event, possibly in the next winter. So it really, you just need to use the tool in the right context. The next question, sorry, there was just an add-on to the previous.
Okay, thank you.
الفكره يا دكتور مش كل الحالات ان يحصل ايروجن على البروفايل فيقوم نقل السيرفر بتاعه مثلا مش بتحصل في بعض المناطق ليها كونديشنز كتير، يعني حالات محدده يعني. فهو كده المديول بتاع الكروس بروفايل ده هو هيشتغل على كده انحر من فوق ويقوم لامي المبنى تحت، بس انا دلوقتي ان انا اخش رفاعيه بس. اول نظام.
The questions from the physical point of view, Engineer Ahmed says that the sandbar is not usually the trend for all shorelines. And نقول ما تخصصش اول الحالات يعني؟
يعني حالات اللي بتحصل ساند بار دي لها دخل بالفايل سكرول بالويب دايركشن، يعني فيلم كبير كده. لكن انا حاسس ان ما اعرفش ممكن حد صححني، حاسس ان الفيو ده هو شغال كده اول من فوق قبل من تحت.
He thinks that this LitPack prof usually takes the sediment from the upper layer, the upper near shoreline to and to perform always a sandbar. He thinks so. He thinks that.
I'm not sure I get the question. So you are saying that are you saying that the LitPack tool has a tendency of forming a bar, although you don't see that in reality?
Yes.
Okay. Well, then you know the alpha that we looked at here would be one tuning parameter where you could smooth out the bar that you're forming and build and distribute the material along the profile. And another parameter would be the wave breaking coefficients, and yet another parameters would be to question if you're using the correct sediment properties, and finally if your offshore wave conditions or the description of offshore wave conditions is correct. But to sort of answer your question now generally, it's a bit difficult. I've not generally experienced that it's always generating too much of a bar. How did you where you experienced that? How did you come up with your input profiles, and especially the bathymetry along towards the shore and the shore face?
Excuse me, can you repeat your question?
The question was then to your student. Sorry, I didn't catch the name. Who experienced a problem with the bar development that he thinks is unrealistic. I just meant it's a bit hard to judge it now on a in general terms. So I just made a few suggestions where you could adjust his parameters. But one question would be how, in that situation where you experienced that, how did you define your input profile and your input sediment definition? Like where. Now, were you very confident on that? Did you have a good local survey, or were there already large assumptions in that?
أنا اللي فاهمه على أي أساس أنت يعني حط
الواقع يعني بنشوفه كل يوم على الشواطئ يعني مش شرط جماعه حتى بتوع الهيئه برضه ممكن يعني
بس هو ممنوع سيرفي يعني انت بتعرف
مش في كل الحالات بيحصل سيرفي يعني معظم 90% 95% من العمل بينتقل مع الليترال ريفت او النشر كارت المناطق الثانيه فيعمل فيها اكشن زي كده. انا كده ما عنديش الابيلتي ان انا اشتغل او احط في تقرير ريزلتس فروم ذا كورسول بروفايل او ما اعرفش الموديل ده اسمه ايه. كده هو اصلا ما عنديش مصداقيه ان هو ينقل اللي هو يعني المره اللي فاتت كنا بنتكلم ان احنا نحسب كميه سيرفنت على البروفايل صوتيا مش مشكله يعني وكاليبريتد يعني. لكن انا اشتغل على حاجه زي كده ده ما شفتش حاجه زي دي في مصر في بعض المناطق القليله جدا جدا. كده اي بروفايل هدخله دلوقتي ممكن حد يصحح لي برضه هيقوم ناحر من السواش اريا ونوثق واعمل لي بار او توم سمعت بعديها بمسافه. فده انا شايف ان ده مش واقعي ومش بيحصل كتير.
بص لازم هو الموضوع بتاع السيمنت ترانسبورت ده هو كومبليكيتد شويه، يعني في جزء من السيمنت بيروح في اتجاه القشور والتاني بيروح في اتجاه القشور، يعني احنا ما نقدرش نحكم عليه نقول كل ده هيروح في اتجاه القشور وكل ده هيروح في اتجاه القشور، فعشان كده ما ينفعش ناخد من منظور واحد نحكم على المكان ده هيحصل فيه كده. يعني عشان نحكم فعلا ده لازم نشتغلها ايه المفروض دي، يا اما نشتغل ليد معاها ليد بروف عشان تطلع نتيجه لنفس البروفايل.
هو ما احنا نحب نحل الليد بروف لوحده Excuse me?
Sorry, I can't follow your discussion now. But, so I don't know if I'm out of context, but one additional component that just came in mind. So looking at the one in Australia, so it is quite typical like that. This summer bar develops in calm periods around the world with sandy beaches where you have an indefinite supply of sand, where the actual transport rates are close to the potential transport rates. But again, in Egypt, where you maybe experience a problem of over-representation of offshore bars, the potential transport is 10 times higher than the actual transport, because you don't have you have very little sediment available. So the cross-shore and that is actually transported along the coast, I think in the dominant direction west to east. Samir, correct me if I'm wrong, but that is only 10% of the potential transport. So there is not much material available for these cross-shore dynamic development. So if now your model develops a bar, then that shows that from the potential transport, it will develop a bar. But maybe that sediment is not even available. So you could, in your model, counteract that by including a non-erodible layer. So if you then, as I talked about, so if you have a non-erodible layer also close to the beach, then that will limit the amount of material that is available to build a bar. And maybe your erodible layer was too close to the surface. Maybe you have more. Maybe you tell your model it has more material available for these processes than it has in reality. That could be an additional point to try to solve your problem.
سؤال المستشفى ايه الحاجات اللي ممكن استخدمها عشان اخدم ريتم استخدم حاجه يعني انا بتقول لي لو انا عندي مثلا دلوقتي مجرى في المينا وعايز احسب كيو جروس فبحسبها عن طريق الليدرز. طب ايه الحاجه بقى اللي انا ممكن يعني الكيس اللي عندي ده استخدم عشان الليدرز؟ ده السؤال اللي انت اصلا يعني هو لو جينا على سؤال هو كده يعني
انت عايزه تقولي ايه الليميتيشنز بتاعت الليد بوك؟
يعني الكيس اللي انا بدرسه
الابلكيشن بتاعته
يعني ايه
الابلكيشن هيستخدم اكروس الشور لاين. Now he was talking about if there are a lot of sediment. The sediment is not too much, which is the case in Egypt. Then most of sediment will go along the shoreline, not on the cross-shore profile. And you can.
انت لو عندك الحاله بتاعتك شغاله بتوضح الحاله دي
يعني الدكتور يكفي عن مثلا عن المفروض
لا هو بص احنا بنسميها
يعني
in reality it is a 2D problem. However, we simplify the 2D problem into two directions. One is longshore and shoreshore. But if the situation is a little bit complicated process, which is a completely 2D process, has discontinuities. ما في يعني في مثلا بريك ديتاتش بريك ووترز مش يعني في شويه حاجات كده يبقى خلاص you have to go to 2D process. لا هي very we can say that we can rephrase the questions. What is the limitations to use the lit prof in our engineering applications?
But the limitations, I guess, are when the assumptions for the model are not met, as you already discussed. So if you have, and that also I showed in my first presentation. So if you have large coastal structures that alter your flow, etc. There's some. Then again, in the coastline evolution, there is some empirical or parameterized formulations to include some coastal structure, that's fine. But like on a large scale, it needs to be sort of a uniform beach. But to be honest, it is then also in real engineering applications, we probably push still the application quite a bit. And maybe I can also show one example of an application where we used it on a project of Denmark, where you can start to argue if these assumptions are all met. But there is in coastal engineering and sediment transport modeling, there are very big uncertainties. So you will always have to judge your results by looking at historical satellite images, by looking on the conditions on the ground. And then after you've implemented like a measure, a structure, there was usually some monitoring program afterwards. So you will have to check if what you came up with is in line with reality. So it is one tool out of many. But I guess the course is now, and although that is not always satisfying, I know that, but when we look at these modeling tools, then probably also allow yourself to then for that course to now dig into that one model and accept, okay, within these this is now the application. And if I am in that box, if I find myself in a project where I am in that box, how does it work, right? Because if we now try too much to link to all the other tools and coastline management, etc., we will also reach the limit of what can be done in 3 days pretty soon, of course. But it's relevant questions. It's a key question to think about the limit.
Okay, well,
I hope and one more comment, what you just said, the longshore transport might be dominant, but you can still have neglectable gradients in the longshore transport, right? So it might be still applicable to also look at your cross-shore profile evolution with the tool that we presented here. But it just might be that there's very little material which is pushed back and forth. Like let's say you have a table, a wooden table, and a little bit of sand on the wooden table, and you can push it back and forth. And to just see where the bar is, the longshore transport doesn't matter as long as the gradient is neglectable, because in the time frame you're looking at it, there's the same material coming in normal to your profile as going out. So after 1 week in your cross-shore profile, you might not be looking at the same sand sediments anymore, but there is still a bar, right? And then if in your model you have more sand than you actually have available to move back and forth on your table, then you can build a bigger bar in your model than you can build in reality. So it's important to define that limiting phase in your bathymetry under which there cannot be erosion, so under which there cannot be sediment supply to your cross-shore profile.
I have a suggestion here. What about we may focus more next day and the third day about these engineering limitations with some examples? What is your opinion about that?
Yeah, we can try that. Yeah.
It will be great for all of us to understand more about the limitations and some applications or some figures to show this. I know you already did in the first day. However, it seems that we need more focus on this point also.
Yeah. All right.
Okay. There is still another opinion, please.
Can I use the LitPack to define the equilibrium profile?
The
Equilibrium profile.
equilibrium. Yeah. The question is it possible to use the LitPack to get the equilibrium profile?
Well, the equilibrium profile is a theoretical, like the empirical formulation that we looked at is an empirical theoretical fit, and also needs to be noticed that the data that has been based on were similar beaches. They were all sandy beaches. So if you are at a beach that is not sort of within that observation data set, that empirical equilibrium profile, the formulation that we looked at on the first day is not applicable. But the other definition of an equilibrium profile is sort of just a time average profile at your local site, at your condition, in your conditions. So you can say that you can say that after you've run your profile evolution over a long period in your local, with your local conditions and all the limitations that there might be with the non-erodible layer, for example, you can perform your own statistics, right? You can look at an average profile, for example. And indeed, on a sandy profile, on a sandy beach that applies to the equilibrium profile conditions, then the profile should also approach that equilibrium profile. That was also used to build some of these tables in the shoreline management handbook that are presented in the first form, where we looked at the Q alpha curves, etc., etc. So to wrap it up, that equilibrium profile in your local conditions might not exist. It might not be approached because there's other limitations.
Mike, the last assessment, please repeat your last
the equilibrium profile that you get out of the empirical equation might not be approached at the actual location you're at, because there might be other limitations, namely non-erodible layer.
اوكي. يعني صعب ان انت تحصلي من خلال البروف على الاكويليبريم، لان ممكن يكون في شويه ريستريكشنز على النون اديتابل ارياز، مش عارف ايه، واخد بالك؟ وان كان هو بيكونسيدر برضه نون اديتابل في الاعتبار.
And it should also, another limitation of the empirical expression for the equilibrium profile is that it was based on experiment data, as I said, for similar beaches, and these beaches also had similar wave conditions. So remember, it was dependent on the 12 hours per year wave exceedance, and there is actually so that might be also a limitation at the site where you are. For the limited to the closer depths, to where the equilibrium profile is applicable. So sometimes your closer depth doesn't exist because you have some other reef, etc. At your local beach you're considering.
Okay.
Yep.
I have a question, which is what is the cases which are not suitable to use such a model, or you can give examples when you discuss the limitation.
Okay, I already proposed that we discuss this next training day. ايوه الاسبوع الجاي ان شاء الله Henrik will prepare some material and some cases to illustrate this much more. Okay. Thank you, Henrik, for your great presentation, and we are looking for the next week session about the limitations and lead line 2.
Yeah. Thank you.
Thank you.
Bye.
Bye-bye.